An introduction to maximum and minimum values. The goals here, one of the definitions of local and absolute maximum and minimum values. Want to understand the extreme value theorem, which basically just says there's going to be a high point and a low point and a closed interval for a continuous graph. Know Fermat's theorem and the definition of a critical number. So this is where the derivatives are really going to come into play for us here and help us find candidates for maximums and minimums. And then understand how to find absolute maximum and minimum values of a function. So we're going to put all this together and see an example at the end. First thing we'll look at here, maximum and minimum values, look at some definitions. And if we look at this graph, you can see that it is on a closed interval. You got the solid dots on the end. And you can also see that there are some highest points relative to the y. We're looking at y values when we talk about maximum and minimum values. So there's a high point and a low point, and then there's some other little peaks and valleys along the graph. So in fact, this point right here, that's the highest y value that the graph will obtain, the function will attain on that closed interval. So this would be the absolute maximum. I'm just going to abbreviate it as abs max there. Now, the lowest point right here at this location, this would be the absolute minimum. And in fact, it would also qualify as what's known as a local minimum, because if you look to the left and the right of that low point, there are things that are higher than it. There are y values that are higher than it. So that's what we would consider a local. And you might be wondering, well, what about the absolute max? Is that also a local? Well, technically, no. The endpoints do not qualify as candidates for local. And probably the best way to think about it right now is just that if you can't look on the left and the right of that point, then it can't qualify as a local. And the endpoints, you can only look on one side of it to compare what's going on one side. So it doesn't qualify as a local. There are some other locals here, though. You got this one here. This little point right there is higher than the points that are around it on both sides. So that would be a local max. And you also have another local min right here. At this point right there, it's lower than things are around it. So we would call that a local min. And again, that other endpoint there doesn't qualify as anything. It's not an absolute, which is all it could qualify for. And by definition, it does not come into play for locals. So let's put this then into words and definitions. So we're going to let C be a number in the domain D of some function f of x. And for a local maximum, the number f of C is a local maximum value of f of x if the f of c is greater than or equal to the f of x's when x is near c. So basically, this is just saying what I showed in the picture. The y values for local maximums are going to be bigger than all the other y values that are right around them. So, like looking up here at the graph at this local max right there, you can see that that y value for that point is bigger than the y values that are right around it. The local minimum, similar idea. So f of c is the local minimum of f of x if the f of c is now less than or equal to the f of x when x is near c. So that's just saying, hey, this y value is a local minimum if it's smaller than the y values that are right around it on both sides, essentially. So again, put this into play up above, but just to get it into words, the endpoints of the graph do not qualify as local extrema, only absolute. They can only be candidates for absolute, the absolute high, absolute low. Otherwise, they do not get counted as locals. All right, so then the absolutes, similar definitions, but instead of just being near a value, it's going to be for all the values. So the number f of c is an absolute maximum of f of x on the domain D if f of c is greater than or equal to the f of x for all x's in the domain. So it's got to be bigger than everything else, or there could be ties. That's why they have that equal to. Absolute minimum, similar idea. The f of c is an absolute minimum of f of x on this domain D if f of c is less than or equal to the f of x's for all x's in D. So it's the smallest y value that you're going to see, and again, there could be ties. So one thing to note before we move into the next concept here is that some functions will have no maximum or minimum values. One example, and let me get this thing to actually stay down here. So one example would be if f of x was x cubed. The x cubed graph looks something like this. And because of the endpoints here, just continuing out to the infinities, there's going to be no absolute max or min. On the right side, it just keeps going up and up and up. And you never say that the max value is infinity. You know, it needs to actually be a number and not just something that's always growing. And similarly, the left side goes down to negative infinity. So there's no absolutes here. And there's no points that qualify as a minimum. Even this little point right here where it kind of flattens out, on one side there's y values that are lower, on another side there's y values that are higher. The definitions of the local max and min do not allow for one side to be smaller, one side to be bigger. Both sides have to either be bigger or both sides have to be smaller in order to give you that peak or valley that you would see with the locals. So this is just one example that has no max or min. There are others out there, but that's kind of what you would see in that situation. No peaks, no valleys, and typically the endpoints keep going up to the infinities, or maybe down to the infinities. Okay, so the extreme value theorem then, looking at this next concept, this basically just says that in a closed interval with a continuous function, you're going to have a high point and a low point that are the absolutes. Which, if you think about it, should make sense. So if f of x is continuous, you don't lift your pencil when you're drawing the graph, will be one way to think of that again. And it's going to be on a closed interval, a to b, then the function is going to attain an absolute max value, f of c, and an absolute min value, f of d, at some numbers, c and d, in the closed interval a to b. So somewhere between a and b, maybe including a and b, you're going to have an overall highest y value and an overall lowest y value when it's continuous. And if you look at this graph, it's pretty easy to see. It's like, okay, well, I start here, and this point actually ends up being the absolute max at the end point, and then you come down and you go back and you go through, and it's like, oh, well, right here, there's the low point. And any graph that you could draw in a closed interval is going to have this idea where there is a highest y value you're going to draw and a lowest y value you're going to draw. And that's basically all there is to the extreme value theorem. So you get your absolute max here, absolute min here. So that's all that theorem says. We're not going to get into the proof of it. It gets a little messy for this class, but the concept intuitively should make sense. Okay, so let's look at Fermat's theorem then in critical numbers, because these are going to be crucial in us getting the absolute max, absolute min, and even locations of locals moving forward. So one thing to note about the locations of local maximum and minimum values in the above graph is that they occur where the derivative, the f prime of c, is equal to 0 for some c value. So if we look up at this graph, notice right here, we got a horizontal tangent line. The derivative would be 0. The slope is 0. Another place, horizontal tangent line, slope is 0. Another place, horizontal tangent line, the slope is 0. All three of those places end up being locations of local maximum and minimum values. So the mathematician Pierre Fermat proved that this was true. In fact, his theorem states that if f of x has a local maximum or minimum at C, and if the derivative exists, we'll talk about this a little bit more later, but in his theorem, the derivative has to exist, then f prime of C is going to be equal to 0. And you can kind of think about it in just an intuitive sense. If the graph goes up, turns around, and comes back down, well, at that place where you went up and stopped and then start coming back down, you got to have a maximum y value. You went up and then you came down. You had to go up to somewhere before you came down, and that would be an absolute max. So, and when that turnaround happens, you're going to have a horizontal tangent line there. The slopes will change from positive to negative as you go up and then come back down. So the converse of the theorem is not true. So that is, if you have the f prime of C being equal to 0, you may not necessarily have a maximum or minimum value at C. And again, the x cubed is a classic example of this. Right here at the origin, you technically would have a horizontal tangent line right here. And you don't end up with an extreme at that point. So if you are going to have a local maximum in there, then it will have a derivative equal to 0, but the derivative equal to 0 isn't always going to be enough to lock you into a local maximum. You have to look at it a little more and make sure that you're going up on one side, down on the other, or maybe down to a minimum and then back up. Okay, so also note that an extreme value may occur at C even if the f prime of C is not equal to 0. It's like, well, when would that happen? Well, a classic example of this is the absolute value function. You got that V shape. And right there at that corner, there's an absolute minimum there, local minimum too, but it is not going to have a derivative there. There's no derivative at that corner. The slope on the left, the slope on the right. If you do the limit definition of a derivative, you get different values. Derivative doesn't exist. So that doesn't exist, we have to pay attention to because of that particular example and others that might be like it moving forward. So these facts then lead us to the definition of a critical number, i.e. a potential location of a local maximum or minimum value. So a critical number of a function f of x is a number C in the domain of f of x such that either the f prime of C is equal to 0 or f prime of C does not exist. So these are just going to give you candidates for your maximum and minimum locations. Locals, absolutes, they just give you candidates. So you look at where it's, the derivative is equal to 0, where the derivative doesn't exist, and there's a chance that you could have the maximum in there. All right, so the closed interval method is what we're going to use to find the absolute maximum and minimum values of a continuous function f of x on a closed interval a to b. Oops, that should be closed there, not round. And we'll go ahead and pick up with the steps and an example of using these steps in the second part of this video.